Thank you very much. Like the chairman said, my name is Nemanja Ilić, and I'm a PhD candidate at the Faculty of Mechanical Engineering, Department of Naval Architecture. So today's presentation will be about some of our latest, let's say, recent project. So the task from the ship owner was to investigate deck houses construction response under severe sea state condition using the finite element analysis. So through this slide, you can see a little overview of the principal dimensions of the subjected ship. On this ship will be mounted deck houses on the upper deck. So the ship is with a length almost 200 meters and the height almost 19 meters, with a deadweight of the capacity of 47,000 tons. So the two subjected deck houses will be mounted on the upper deck, like here on this position. Those are the 3D models of the deck houses, which will be needed to be applied, let's say, on the upper deck, 3D model of the deck houses. Here you can see on the general arrangement of the ship clearly those positions where the deck houses will be installed. So we have on the left side of the ship, port side of the ship, port side deck houses, and on the right side, starboard deck houses. Here is also a view of the midships section with the arrangement of the deck houses. So the deck houses will be arranged like this in this position with a view to the fore part of the ship. Here is a little overview to have in mind the sense about the dimensions of the deck houses. So the length of the port side, the bigger deck houses is the 7 meters, comparing to the other side, to the starboard deck houses, which is 5.3 meters. So what is the purpose of those deck houses? Behind this IMO resolution, which has been adopted first time 20 years ago, it's called for approval of ballast water management system. So the story behind this IMO code is that you cannot take water from the sea and put inside of the tanks without any treatments. Why? Because that was identified as one of the 4 greatest threats to the world's ocean. So you have to prevent of invasion of harmful organisms and pathogens to new environments. For example, you cannot take water from the Black Sea and then the same water without the treatment release, for example, in the Adriatic Sea. So required finite element analysis. Regulatory bodies for the ships generally require finite element analysis when existing ship structures are modified, or in this situation, non-conventional structures are added on board. So those deck houses are subjected to various load combinations that simulate extreme conditions ship can encounter. You will see in the next slide, one of the next slides, the video about ship on the roof sea. Let's say when you will take a the loads also considered consist of the weight of the structure and also its internal equipment, because also that equipment subjected inside of the deck houses will be needed to, let's say, transfer to the force and to be applied inside of the finite element methods inside of the software. So we have also to simulate a dynamic loads such as wind velocity, seawater pressure on the walls of the deck houses, and also acceleration due to ship motions. Here is a little overview also of the deck houses on its internal equipment inside of the deck houses. So we have, like, for example, foundation of the tanks and generators. On top of the deck houses, we have some inlet and outlet of the ventilation. So every part of this equipment have to be applied inside of the software as a force which is attached to the subjected area. The total weight of its equipment is 16.4 tons. The same situation is for the other deck houses, starboard deck houses. where you have some equipment inside of it. Here is an overview of the construction of the port side deck house, and also starboard deck house. So the finite element methods. So two finite element methods models are produced each for each of the deck houses, and they are provided according to those principles. So all structural members from the 3D model influencing the structural integrity of the deck houses are considered, like we saw on the previous slide, like shells, girders, stiffeners, or the brackets. All structural members are modeled as a thin plate elements, dominantly using the 4-node plate element, but in some situation we cannot, let's say, attach or idealize the surface area with the 4-node plate elements. We use the 3-node. And the average dimension of the thin plate elements are between 100 and 150 millimeters. This is an overview of the idealized geometric 3D model of the port side deck houses. So this port side deck houses has 22,000, almost 400 finite elements. This is a little overview from the inside of the deck house. So you can see when I thought about finite element method, I talked about the 3-node plate element. This is situation for this triangle, let's say brackets in the end of the bottom floor of the house. Because of the geometry of this triangle brackets, we couldn't apply the 4-node, we applied the 3-node. Same situation for the starboard deck houses, idealize the 3D model with the mesh. It has 14,000, almost 14,000 finite elements. Also overview from the inside of the houses. So now the material properties. So it's been used mild steel grade A with the yield stress of the 235 megapascals, and the theory which has been applied is the thin plate theory of small deformation, widely used for the ship structure due to nature of the sleddiness of the ship structures, like these shells, girders, and the stiffeners. Material behavior has been modeled as a linear elastic, mostly because of the demand, let's say, for the classification societies due to criteria given by them, because they said if you use finite element analysis for the direct calculation, you have to apply this criteria, which means that for meter stress of each finite element shall not exceed 90% of material yield strength. Now we'll see a connection of those deck houses with the deck. This will be important for the boundary conditions. So you can see both of the deck houses are strengthened with some primary construction with the deck. So the boundary condition applied, idealized in this situation. In both of the deck houses, the bottom nodes of the foundation structure are constrained and simulated to be clamped. That means that degrees of freedom of all of those nodes and the end of the foundation with the connection of the primary construction of the deck are set in 0, translations and rotations. So now this slide will be a little, let's say, overview and simulation about which loading condition we need to apply through regulatory bodies task, let's say. So yeah, you can see on this slide the ship on the roof C. Regulatory bodies require from us to apply sea water pressure, wind velocity. Also, you can see that there are big acceleration due to ship motions. Most of the biggest acceleration here is going in the line with the z-axis. loads and loading cases. So design pressure from the sea water, which is applied to the walls of the deck houses. We need to apply the design pressure for each of the four walls, and it is applied using this formula, where the H is derived from the ship particulars. Also, the wind pressure. The wind pressure is derived from the velocity of the wind from the 63 meter per second. So we have 4 loading conditions, loading cases. For each of the loading cases is subjected to one of the 4 wall of the deck houses. For example, for the aft wall, we need to apply the pressure on the wall, which is 2.43 kilopascals. Also, the acceleration to deck house motions, the acceleration need to be applied to the entire model. That means to do all nodes in the model. So acceleration I obtained for the most critical conditions ships can encounter, like you saw on the previous slide about that video. Also, 4 loading cases, each of the walls. For example, for the aft wall, we have an acceleration going in the line with the x-axis, which is half of the gravitational acceleration, and in the line with the z-axis, it's a double gravitational acceleration. So this is a summary about 4 loading cases and the type of the loads applied and derived from the task given from the regulation bodies. We have design pressure, wind pressure, and acceleration, also plus the local weights of the structure and the internal equipment inside of the deck houses. Everything of it is multiplied by 3 Scantley cases. So, for example, for the first loading case, we have also 3 Scantley cases, which is the thickness variations. Those on this slide, you can see now two diagrams, each of the deck houses. So on the horizontal axis are the loading cases, and for each of the loading cases, like I said, you have 3 Scantley cases. When we apply the criteria given by the classification society, we can see that, for example, for the port side deck houses, almost for each of the loading cases, the Scantley cases, this port side deck house didn't pass criteria. So we can say that these deck houses failed the criteria given for the classification society. When we talk about starboard deck houses, we will see that just for the Scantley case 1, for the lowest one, if we are talking about the thickness of the elements, so we will start the optimizations. I will show how it has been done optimization, particularly for this Scantley case 1 for each of the loading cases. If you take a view about this critical form measure stress for the loading case 3 and the Scantley case 1, on this slide, it's shown up how is stress distributed on the walls. For example, we have 3 critical positions. First one is here on the right side of the house. This wall is near to the sea, so we have here the highest, let's say, the critical points, critical form measure stress, which is almost 280 megapascals. Also, we have one position here, which is above the limits given by the criteria from the classification society here on the edge, and also down on the bottom due to some internal weights because of the equipment subjected inside of the deck house. So this is a starboard deck houses before optimization without walls, and the photo on the right side is the after optimization. So what we added brackets here at the edge of those 2 walls, transverses on the right side near to the sea. We needed also to increase the thickness of those brackets from 4 to 5 millimeters, and of course double plates on the floor. So those are the results before the optimization, and after optimization the results are like this. So now we can say that we optimize this optimize this starboard deck house, and we pass the criteria given by the society, classification society. Oh, now is the how it's looking inside from the software, finite element software. You can see now that their stress distribution is much more smoothly after applying those, for example, those transfers on the right side, also here at the edge because of the brackets, and down at the bottom, at the bottom of the house. So now we have the the maximum critical, let's say, stress estimated from the finite element method is somewhere a little bit above 200 megapascals. So that will be that. Thank you for your attention.